So here we're asked to find the equation of a function having been given its graph and understanding the transformations from the parent graph that it's based off of. And then we want to write that function of that graph that we see in two ways. We want to write it in terms of x and in terms of f of x. And we'll talk about the difference between those in just a bit. But first, we want to identify what type of function are we working with. In this first case, we have a v-shaped graph, so hopefully that's familiar to us as being a absolute value function. So our parent graph is absolute value of x, or maybe better than that, we can write f of x equals the absolute value of x, establish that that's our parent, f of x. So we want to see how is this graph different from its parent. So if we recall, the parent graph looks like this, where it's got slopes of 1 and -1 on the sides, its vertex is at the origin, it's opening upwards. So just sketching that in for us so that we can have that to work with as a guide. So clearly our vertex has moved, and so we can say that we've translated, looks like we've gone to the right 2 units, and then we've also translated down 1, 2, 3, 4 units, so down 4. It does not appear as though we have any dilations. If we look at the slopes of the sides of the graph, we're going up 1 over 1 on both sides, so that's consistent. So we have no dilation to speak of, neither in the horizontal nor the vertical direction. And then we don't have any type of reflection. Our graph is still opening upwards, as is our parent graph, so we've got nothing in that respect. So we want to now write the function. I'm actually going to start with writing it in terms of x. So we want to write the actual equation of the graph that we see. So my function g of x is going to be equal to, now I have to incorporate these two changes. To get a shift to the right 2, that means we're going to add or subtract a number on the inside of the absolute value. And hopefully we recall from the previous video that when we're moving in the horizontal direction, it shows up in the equation as the opposite of the direction that we would expect. So the opposite positive negative sign that we would expect. So since I'm moving to the right 2, I would normally associate that as being positive, so I'm going to put that in as -2. But then in the vertical direction, our translations go the direction of the positive negative sign that we see. So on the outside of the function, to get a movement down 4, I'm going to have a -4. And if we have any doubts as to whether or not we have that correct, we can just test a point. So the coordinates of the vertex of our v here are 2, -4. We can just double check to make sure that when we plug in 2 for x, we get -4 as an output. And indeed we do. 2 minus 2 is 0. Absolute value of 0 is 0. 0 minus 4 is indeed -4. Now for writing the function in terms of f of x. So this is where we're going to write the function g of x, not with the absolute value in there, but instead we're going to write it with f of x in place of the absolute value of x. So that means that our function could have been anything. It could have been absolute value of x as we see here, but this could have been an x squared graph, it could have been an x cubed graph, it could have been anything else. So in this case here, I'm going to write f of, instead of absolute value of x, I'm going to write f of x, but it's going to be just like this, f of x minus 2, and then the -4 on the outside. So this is just writing it in kind of a generic format, a general format, where I wouldn't have even had to have known what the original function was. I just know that I'm going to take whatever my original function f of x is, I'm going to translate it to the right 2 units and down 4 units. In the second example, we're looking at another function where it's an absolute value function. So we've got that V shape again. So my parent graph is going to be absolute value of x. Now, to determine the translations, I'm just going to pay attention to the vertex. I can see that my graph is upside down. I can see that the slopes of the sides are different. But for the translations, I'm just concentrating on the vertex. So in this case, the only translation I have is the graph is going up 2 units. So I've got that. For the dilations, so normally the slopes of the sides are 1 and -1. But Now, if I look closely, I'm going down 1 over 2, down 1 over 2, and I'm doing that on both sides. So that means the slopes of my sides are positive and negative 1/2. So that means my dilation factor, so instead of going down 1 every time, I'm going down half as far. So there's a couple ways that I could describe it. I could describe it as being a dilation in y by 1/2, or we could say it's a dilation, try that again here, we could say it's a dilation in x by 2. So again, the reason is for the dilation in y by 1/2, we're going down half as far as we normally would. If I go over to the right and left 1, I'm only going down 1/2. I go to the left and right 2, instead of going down 2, I'm only down 1. So that's one way that we could characterize it. The other way we could look at it is the graph is being stretched in the horizontal direction. We're going to the right and to the left twice as far as we normally would. So that would mean that we're being stretched, we're being pulled to the left and right by a factor of 2, but that would show up in our equation on the inside of the function as a 1/2. My advice is almost always, whenever possible, use a vertical version of the dilation instead of a horizontal. It's just easier to interpret. We don't have to remember that we would have to flip this into 1/2 when we put it inside of our equation. So given a choice, which pretty much we always are, use the dilation factor as being in the vertical direction instead of the horizontal. It's just a little easier. But to continue on, we do have a reflection in this case. So the graph is reflected, we could say, across the x-axis since it's going down instead of up. So we have a reflection in the x-axis. So now we're ready to write our function. We've identified the translation of up to, the dilation in y by 1/2, the reflection in the x-axis. So now we want to write this function. And again, I'm going to start with the function in terms of x to begin with. So I'm going to have g of x equals. Now, if I want, I can kind of start with my absolute value of x, and then I can build around it. So if I have a reflection in the x-axis, that means I need a negative on the outside of the function. So negative out there. I also have this vertical dilation of 1/2, so I'm going to need a 1/2 on the outside of the function. I have no translation to the left or to the right, so I don't need anything inside of my function there. But then finally, I do have this vertical translation of 2 units, so I need a +2 on the outside. So if I have any doubts as to whether that's correct, I can test a point. So right here, our vertex is at 0, 2. If I plug in 0 for x, I indeed get 2 as a y value as an output. So I feel pretty confident that that equation is correct. And then the last thing I need to do is to write my function in terms of f of x. So this is just where I'm going to replace the absolute value of x with f of x. So I'm going to go g of x equals negative 1/2 times f of x. So again, this is just this general format so that it could be applied for any function I might be working with. And then of course I need the +2 for that vertical translation.